Welcome back, everyone, to Flight Vehicle Dynamics. This is lecture 4 in week number 2. So today we're going to talk about rotation rates. So far we've seen what the Euler angles are and how we can define a rotation matrix to go from one reference frame to another. In particular, last time we saw the very common rotation sequence 3-2-1. So we first apply a rotation about the local z-axis of an angle psi, then we rotate about the new y-axis about with an angle theta, and then finally we rotate about the new x-axis of an angle phi. The three Euler angles in the 3-2-1 sequence are called yaw, pitch, and roll angles. And in the example that we saw in the previous lecture, we found, or we assumed that such angles were constant. So the orientation of the body frame with respect to the inertial frame is fixed. So usually, since the LHLV is considered inertial for our applications, if the body frame of reference has a constant orientation with respect to the LHLV, well, technically also the body reference frame is inertial. But as this is only a very particular case, and this is only valid when the three Euler angles are fixed, this is usually not the case. In fact, the body frame of reference changes continuously its orientation with respect to the inertial frame of reference. So the Euler angles are not constant, but they are time variant. And the body frame of reference is thus not inertial. So whenever we write or we refer to our body reference frame, then of course we have the origin, but now the versors that define the direction of the three axes of the body reference frame, they're not fixed, but their orientation change with time. So B1, B2, and B3 are a function of time. And well, consequently, also the Euler angles, psi, theta, and phi, are also functions of time. And the orientation of the body reference frame with respect to the inertial frame of reference change for different times t. So in other words, we have that the body reference frame rotates with respect to the inertial frame of reference. So all this to say that. So since the orientation change, well, this process will happen at a certain speed. So in this case, we're only dealing with rotations. So the question is, what is the actual angular speed or angular rate at which the body frame of reference rotates with respect to the inertial frame of reference? Now here, before answering this question, I want to point out a few things notation-wise. So we're gonna perform a slight change in notation. In fact, so far the local horizon, local vertical frame of reference has been referenced to as L, with the three versors being L1, L2, and L3. But now, since LHLV is inertial when describing the motion of aircraft, we will just simplify by simply indicated with I as in inertial. So we don't really care that it is actually the LHLV frame of reference. It could be any inertial reference. So we're just going to refer to it as I with origin in O and with the three versors I1, I2, and I3. So this is the first thing. Instead, the body reference frame will still be indicated with B and sharing the same origin, and with the three versors B1, B2, and B3. Now there's an implicit assumption here, and I'm not going to write it down all the time, but B1 and B2 and B3 are functions of time. So again, technically speaking, it would be more precise to indicate them like so, but this is implicit. Now, second thing about notation. So now we're gonna see how we express the actual angular rate. So the angular velocity of the body frame of reference with respect to the inertial frame of reference. So we're gonna write this velocity vector, angular velocity vector, in this manner. So the velocity vector, when it deals with angular rates, so it is an angular velocity, is usually indicated with small omega. And of course, it is a vector, so we have the vector sign. Now we have other two symbols, or other three actually. So the superscript means that this is the angular velocity of the body reference frame with respect to the inertial frame of reference. And of course, if we wanted the angular velocity of the inertial frame of reference with respect to the body frame of reference, we would simply write omega of I slash B. But we're really interested, and that's just the opposite of this one, but we're interested in determining the angular velocity of the body frame of reference with respect to the inertial frame of reference. It makes sense because the inertial is fixed. So it's the body frame of reference that really rotates around the inertial frame of reference. Of course, if you are on the body frame of reference, you think that the body frame of reference is fixed, and then you can see the inertial frame of reference rotating about it. So it really depends on the perspective. But it is more convenient, in my opinion, to think about the inertial frame of reference as fixed and the body frame of reference rotating about it. So it is more logical to define the angular velocity of the body frame of reference with respect to the inertial one. Now, we also have at the subscript here, and this is what we've already seen for all vectors, and that it expresses the frame of reference in which the coordinates refer to. So in this case, we have the angular velocity of B with respect to I expressed in a C reference frame coordinates. Of course, here I use a third general reference frame because you don't have to express the coordinates of omega exclusively in the body frame of reference or in the inertial frame of reference. You can use a third frame of reference. Most of the times we're really interested in expressing omega in either the inertia or the body. So that C is going to be equal to either B or I. But this is the general notation. Okay, so as I anticipated, the angular velocity is a vector, so it will have three components. And the components obviously depend on the frame of reference C. So another way of seeing the angular rate, well, or at least how to make sense of that superscript, you can think about it as the angular rate of frame B measured in frame I. So if you have an instrument in the frame of reference I and you measure the angular rate of B, then this angular velocity is what you would actually measure. And then lastly, when it comes to angular velocities, the basic rule of adding relative velocities apply. So what does that mean? If we have, now we don't really care about the coordinates of the vectors, so which reference frame they're expressed into. So this is just a general vector. So the velocity, the angular velocity of frame B with respect to I can be decomposed into, well, it could be any kind of angular rates, but in this case, we're referring to other two reference frames, I double prime and I prime. So the angular rate of B with respect to I is equal to the angular rate of B with respect to I double prime plus the angular rate of I double prime with respect to I prime, and then finally plus the angular rate of I prime with respect to I. So the three angular rates on the right-hand side of this equation are just relative velocities, so relative angular velocities. So you can use as many intermediate reference frames as you wish. In this case, I've used 2 extra reference frames. And why is that? Well, it's because we've talked about the overall coordinate change or rotation between I and B as a composition of 3 elementary rotations. So when we go from I to B, we actually, it's like we were stepping into 2 intermediate reference frames, I prime and I double prime. And now I'm going to show you a summary of, or all possible, I would say, coordinate changes and angular relative velocities for the specific 3-2-1 sequence of rotation. And so now it will probably make more sense why we use the I prime and I double prime. So this might look complex at first sight, but it's really meant to simplify things, if you believe it or not. So let's try to read this schematic. So in the center line, we have the 4 reference frames. So we have the 2 major ones that we're really interested in, which are the inertial frame of reference, I, in the first place, and then I jump directly to the body frame of reference. So the other 2 frames of reference, I prime and I double prime, and they're just used to get step by step from I to B. So if we go step by step, then we follow, for example, this arrow over here. So we know that a vector expressed in the I prime coordinates is equal to a vector, so the same vector in the I coordinates, but now we have to pre-multiply it by the elementary rotation about the z-axis. So we're going to perform a rotation R3, and the angle is going to be psi. Now we have a vector expressed in the I prime coordinates. What if we want to go from I prime to I double prime? Well, similarly, we just jump from I prime to I double prime. Therefore, the same vector expressed in the I double prime coordinates is equal to the vector in the I prime coordinates. And now we perform the second elementary rotation. So we have to pre-multiply by R2 of theta. And keep in mind that here we're referring to the 3-2-1 sequence. So that's why we first performed the rotation about the z-axis. Now we perform the rotation about the y-axis. And finally, the last step, going from I2 to the body frame of reference B, we have that the vector expressed in the I2 prime coordinates, when pre-multiplied by the rotation matrix R1 of phi, will give us the vector expressed in the body reference frame coordinates. Now you can also skip one step and go directly, for example, from I to I double prime. So let me just clear up a little bit here. All right, so let's say we want to go directly from I to I double prime. So we have to follow this path. So we have that a vector v expressed in the I double prime coordinates can be obtained by selecting a vector in the I, so in the inertial reference frame, and pre-multiply it by two rotation matrices, the two elementary rotations. So we have first R3 and then R2. Remember that we're reading from right to left. Logically, that would make sense. And then, of course, if we want to go to I double prime to B, we still have the rotation that we described earlier. So you can see that how this works. And well, the last thing that the other combination would be if we go from from I to I prime first, and then we jump from I prime to B. And so you can read the coordinate transformation of these two rotations. Finally, if we just want directly to go from I to B, well, we would have, like we saw last time, taking a vector in the I coordinates, you would have to multiply it by the three elementary rotation matrices and get the same vector, but expressed in the body reference frame coordinates. I know maybe I'm going too slowly, but I really want you guys to be familiar with these things. All right, so now if we take a look at what happens in this side of this schematic, here I've written down the angular velocities and the relative angular velocities between one frame and another. So for instance, we have that this angular velocity is the angular velocity of the I prime reference frame with respect to the I reference frame. And then we have this is the angular velocity of I double prime with respect to I prime. So if we wanted to go directly from I to I double prime, then we would have to consider the omega from I double prime to I, which is the sum of the two angular velocities that we just saw. And so you can proceed in a similar way for from going to any reference frame to another. So of course, we have the general case. If we just want to go from I to B, then you have the overall angular velocity that is the sum of the three relative angular velocities as we saw earlier. Okay, I hope this helps. So just make sure you get familiar with this. So now let's take a look at what actually happens when we go from the inertial frame of reference to the body frame of reference. Let's see how we can actually construct, this angular velocity vector. And we're going to do it in a similar fashion as we did last time when we constructed the rotation matrix. So we start from here. So we have the first rotation. And so we're switching from the inertial frame of reference in the expressed with the yellow versors to the I prime frame of reference expressed with the dark orange versors. So the first rotation happens about the z-axis. So you can see the rotation is about the z-axis. And so we have the angular velocity, that is this vector over here. And this is the angular velocity of I prime with respect to I, because we're going from I to I prime. So it's I prime rotating about I. And the vector, when it indicates an angular velocity, it usually has two arrows. So if you're referring just to translational velocities, those vectors only have one arrow. And when we're talking about angular velocities, and when we draw the vectors, they have two arrows. So you know already what it means. And of course, if in this case it points upwards, it means that when you look at things from above, the angle or the rotation happens counterclockwise. All right, so what is the value of omega of I prime with respect to I? Well, that is simply the rate of change of the angle psi, so psi dot. And in which direction? Well, that is aligned with the z-axis. So the versors that we're going to use is I prime 3. But we could also write it as psi dot times I3. And why is that? Well, simply because I3 and I3 prime are the same versors. You see, they are the same over here. But I'm going to express, so I'm just going to choose I prime 3, and we'll see later why. Okay, so now let's move on to the second elementary rotation. So now we go from the I prime frame of reference, so from the dark orange versors to the I double prime reference frame, which is indicated by the green versors. And now the rotation happens about the new y-axis. Okay, so the rotation, as you see, happens about the new y-axis. Why do I say the new y-axis? Because I don't want you to think that the rotation happens about I2. That doesn't exist anymore. So now we've changed from I2 to I2 prime. So the second rotation happens about I2 prime. And so you see that I2 prime is going to be equal to I2 double prime. And what changes is actually the direction of I3 and I1. So I3 double prime is going to be different from I3 prime, and there's going to be an angle equal to theta between the two, and same thing between I1 prime and I1 double prime. So in this elementary rotation, what is the expression for the angular velocity? So of course here we're referring to the angular velocity of I double prime with respect to I prime. And that is simply theta dot in which direction? Well, in the direction I2 double prime. As I said earlier, this could also be written as theta dot in the I2 prime direction, because I2 prime and I2 double prime are the same versor. Okay, so now let's move on to the third and final elementary rotation. So now we are switching, or we are rotating, I should say, from the I double prime reference frame. So from the green versors, we apply a rotation about the new x-axis in order to get to our body frame of reference, which is indicated by the purple arrows. So now the rotation happens about the I1 double prime or the B1 versor, because of course they are the same. And so the I2 double prime will rotate into B2, and the I3 double prime versor will rotate into B3. And you can see very easily that the angular velocity for this elementary rotation, so omega b with respect to I double prime, so the angular velocity of the body frame of reference with respect to the intermediate frame of reference I double prime is equal to phi dot in the B1 direction. So now we've found an expression for the three intermediate rotation rates. So if we sum up these three contributions as per the rule of relative velocities, we find the overall angular velocity of the body frame of reference B with respect to the inertial frame of reference I. That's very good. We haven't really specified any coordinate, so we don't really care about the coordinate system. But you see that, well, we have to use that. So let's express all these vectors with respect to the body reference frame. So in other words, let's use the body reference frame to write down the coordinates for these vectors. In order to do so, we have to express all the vectors with respect to the body frame of reference. In particular, we have I3 prime that has to be written in the body frame of reference. Then we have I2 double prime, and then B1. Well, you see that these versors, especially I prime and I double prime, are not naturally expressed in the body frame of reference. So they're not unit vectors. So we have to rotate them so that they are expressed indeed in the B coordinates. So let's start with the I3 prime. And how do you change coordinates? Well, you use these relationships over here, and you find which rotation matrices you have to use to switch from one coordinate system to another. So in this first case, we have I3 in the I prime reference frame, sorry, over here. And we want to find the same vector, but expressed in the body frame of reference. So let's see what RBI prime looks like. Well, let's go up here. So we have to go from I prime to B. So we have to follow this path. So you see that the rotation matrix is equal to R1 of phi times R2 of theta. And what is this versor over here? So what is I3 prime in the I prime reference frame? Well, it's I prime in the I prime, so it's just a unit, it's an elementary unit vector 0, 0, 1. So in other words, now we have to rotate 0, 0, 1 into the body frame of reference. So we have to pre-multiply it by R1 and R2. So we find eventually that its coordinates in the body reference frame are minus sine of theta. Then we have sine of phi times cosine of theta and cosine of phi times cosine of theta. Okay, so now we have an expression for I3 prime in the body reference frame. Now we have to do the same for the other two versors. So now we have I2 double prime that has to be expressed into the body reference frame coordinates. So how do we get from I double prime to B? Well, let's also take a look at our useful summary over here. So we have that from I double prime, we go to B by applying a single rotation about the x-axis and the rotation of the angle phi. So going from the I double prime I2 to the body I2, we have to apply this rotation about the x-axis. And the expression for I2 double prime in the I double prime reference frame is simply 0, 1, 0. So here the multiplication is a little bit easier because we only have one elementary rotation matrix. So we find that I2 double prime in the B coordinates is simply 0 cosine of phi and minus sine of phi. Now what about B1? Well, B1 in the body coordinates is very easy. We don't have to rotate because we're already in the reference frame that we are interested in. And the versor, the coordinates are simply 1, 0, 0. Okay, so finally, we have all the ingredients to write the angular velocity of the body frame of reference with respect to the inertial frame of reference written in the body frame of reference coordinates. And so we have these three vectors. We just sum them up, and we can actually write it in a matrix form. So we have the angular velocity with three components: omega b1, omega b2, omega b3. So these are the components, once again, of the angular velocity of the body frame of reference with respect to the inertial frame of reference. So we have these two elements in the right-hand side of this equation. The first one being a matrix, which is usually called B of theta, but in this case, theta is a vector, and it actually indicates all three Euler angles. So theta vector is actually c, theta, and phi. And then it multiplies this other vector of c dot, theta dot, and phi dot. So here I just want to tell you two things. So first of all, the psi dot, theta dot, and phi dot are called the Euler angle rates. Those are the rates at which the Euler angles change. And although the vector to the left, so the angular velocity of the body frame with respect to the inertial frame, has a physical meaning, the vector to the right, so the vector of the angle rates, the Euler angle rates, does not have a physical meaning. So the vector itself does not represent anything in particular. The other thing that I want to point out is that this matrix B is not a rotation matrix. So it doesn't have the nice property of its inverse being equal to its transpose. That is not the case. And also, this is not a unique matrix, but it depends exclusively or particularly on the sequence of elementary rotation. So in this case, we have a 3-2-1 sequence of rotation. So we're going to get this particular B. What if you had another sequence? Well, you will end up with a different B matrix. As a matter of fact, I suggest you repeat this analysis for the 3-1-3 case, and you'll see that the B matrix is going to be different. Furthermore, we have that if we take the inverse of the B matrix, well, you'll see that we will end up with this 1 over cosine of theta. And whenever we have things at the denominator, well, we're going to have some troubles. And you can see that cosine of theta goes to 0 when theta goes to plus or minus 90 degrees. So that inverse of the B matrix will just blow up. Will go to infinity. So what is the physical meaning of having theta equals to plus or minus 90 degrees? Well, you recall that theta is the pitch angle. So it pretty much tells you how the nose of the aircraft is pointed. Okay, so if theta is 90 or minus 90, it means that we're going straight up or straight down, which is not usually the case for a commercial aircraft. It will never fly with a pitch angle close to 90 degrees or minus 90 degrees. But that is definitely the case for rockets, because a rocket will just go upwards, at least in its first stages, exactly vertically. So the pitch angle is indeed 90 degrees. So how do we solve this problem? Well, there are a few solutions. We're going to see them later on, but just keep in mind that every sequence of rotations will have this problem. So it really depends on what you're describing. In the case of flight for aircrafts that stay far away from the plus or minus 90 degrees in terms of pitch angle, well, that is not really a big deal, but we cannot use this sequence of rotations, so this matrix, to describe all types of flights. So we will have to use other rotations or use other things, and I'm already anticipating a solution is using the quaternions, but I'm going ahead, and so don't worry about it for now. But just keep in mind that there is a singularity, and that is a problem. All right, here, and you can, if you have the angular velocity and you have the instantaneous Euler angles, you can form the B matrix, get the inverse, and then you find the Euler angle rates, C dot, theta dot, and phi dot. All right, so it will take you maybe a little bit to digest this, so make sure that um, you go over these notes, and then I'm gonna post tomorrow some more detailed handouts about this. But make sure that you understand the concept. And if you don't, please email me, ask me questions, come to office hours, because you really don't want to stay behind in this course. You want to be on top of the material, because if you just don't study and don't follow for a week, well, you're gonna get lost, unfortunately. So make sure that you follow and you watch the lectures, and of course make sure you understand. And if you don't, just come ask me. Don't worry, there are no stupid questions, okay? So I'm not gonna judge you. I'm just here to make sure that you guys understand. All right, so now let's put into use what we've learned so far, because remember now our objective is to describe the motion of a point mass particle. And as you may recall, I told you that we were going to start with the kinematics. So the kinematics is the relationship between the position, velocity, and acceleration vectors, referring to a particle P. And in the end, our goal is to find an expression for the inertial velocity and acceleration, especially because only the inertial acceleration can be used to apply Newton's law. Or, in other words, when you write down Newton's law, just very quickly, what you all know as F equals m times a, that acceleration has to be inertial. So now we have to find a way to express this inertial acceleration given an inertial frame of reference, a body frame of reference, and well, let's see how it's done. In this lecture, we're not going to get to the actual expression for the acceleration. We're going to see that next time. We're just going to get to the expression of the velocity of the particle with respect to either the inertial frame of reference or the body frame of reference. Okay, so you see over here, I drew the two frames of reference that we are usually referring to, the inertial frame of reference with its orange versors, then we have the body frame of reference with the purple ones. And then finally, we have the position vector of the particle P. So the position vector is a vector that goes from the origin of the frames to the particle itself. And then I've also indicated the overall angular velocity of the body frame of reference with respect to the inertial frame of reference. So other considerations here. So, well, the position of P is a function of time, so it varies, generally speaking, of course. Then we have the versors of the I frame of reference. So they are time invariant with respect to the inertial frame of reference itself. Of course, they're fixed with it. They actually define the inertial frame of reference, so they do not change. But they are time varying with respect to the body frame of reference. And why is that? It's because the body frame of reference itself moves about the inertial frame of reference. So I1, I2, and I3 move with respect to B. If we are fixed in the B frame of reference, we see I1, I2, and I3 move. Well, a similar conclusion can be drawn for the B1, B2, and B3 versors, which are time invariant with respect to the body frame of reference because they're fixed with the body frame of reference itself. But of course, they are time varying with respect to the inertial reference frame. The other thing now is the velocity of P. Okay, so we can express the velocity of P, well, with respect to, we have two frames of reference. So we can express the velocity relative to the inertial frame of reference, and we're going to indicate it with V and superscript I. So this doesn't have anything to do with the coordinates. It's just the velocity of P with respect to the I frame of reference. So V is the derivative time-wise of the position vector. So it's going to be dr over dt, but relative to I, so we're going to have a superscript on the left-hand side, which is I, and that will remind us that we are referring to the I frame of reference. So the velocity with respect to the I frame of reference. So similarly, we can define the velocity of P, so of the particle P, with respect to the body frame of reference. So we're going to have V superscript B, and that is the derivative of the position vector R, of course, derivative with respect to time, but refer to the body frame of reference. So VI and VB are not necessarily the same vector. Okay, so VI is the so-called inertial velocity, whereas VB is the non-inertial velocity. Okay. Well, some of you might think, well, you just said that you're interested in inertial velocity and inertial acceleration. So why are you even bothering expressing the velocity with respect to the body frame? Well, that's simply because the velocity in the with respect to the inertial frame of reference is much harder to measure. So it's much easier to measure the velocities in general with respect to the body frame of reference. So that's why we're going through this analysis that you'll see. Otherwise, if it was easy just to get the velocity, the inertial velocity, well, then we're done. We wouldn't really care. But that is not the case, unfortunately. All right, so let's take a look at things from the inertial reference frame perspective. First of all, let's write down the position vector. So the position of P in the reference frame I, and we use the I coordinates. Okay, so we use coordinates in the inertial frame of reference. So R in the I coordinates is just RI1 in the I1 direction, RI2 in the I2 direction, plus RI3 in the I3 direction. All right, so now let's take the derivative of this position vector and let's get the velocity vector, the inertial velocity vector, and we keep that in the I coordinates. So let's take the derivative of the vector. So we're going to have the derivative with respect to time of RI1 in the I1 direction, then the derivative of the second component and the third component. Now, what is the derivative of RI1 in times I1, the I1 versors? Well, we have to apply the chain rule of derivation. So we have the derivative of RI1, which is just a scalar, it's not a vector, it's just a component. So we have dr I1 over dt. times I1 plus RI1 times the derivative now of the versor di1 over dt. So you can see right away that this is 0. di over dt is 0. And why is that? It's because the versors I do not change. They are time invariant with respect to the inertial frame itself. As I said earlier here, I1, I2, and I3 are time invariant with respect due to the inertial frame of reference. So the derivative of, so the change, when you're talking about the derivative of something with respect to time, you're calculating how much this quantity varies with time. So if the quantity is time invariant, then its derivative with respect to time would simply be 0. So di1 over dt and di2 over dt and di3 over dt with respect to I are 0. So what we're really left is with is the other three, it's only 3 elements, and these are, well, indicating dri over dt with r dot I, we simply have that the velocity, the inertial velocity of P in the I reference frame coordinates is r dot, r I1 dot in the I1 direction, plus r I2 dot in the I2 direction, plus r I3 dot in the I3 direction. So all this, technically, it could have just put a dot over here, and you would get from, you would go from the position to the velocity vector. But it's a little bit more sophisticated than that, so we had to go through all these steps. All right, so now we have an expression for the velocity of the particle, the mass particle P. Of course, velocity with respect to the inertial frame of reference. So we have the inertial velocity expressed in the inertial frame of reference coordinates. Now let's take a look at things from the body reference frame perspective. So we have the position vector. Position vector is the same, but now we're going to write it down in terms of coordinates in the B reference frame. And once again, we're doing this because it's usually more convenient to express the position of P with respect to the body reference frame or the wind reference frame, in this case, the body reference frame. So anyway, with respect to a non-inertial frame of reference rather than a frame of reference that is fixed. Okay, so now let's take the derivative of this position vector, and by doing so, we're finding the velocity of P, the non-inertial velocity of P in the body frame of reference coordinates. So we're doing something similar to what we did earlier. We have the chain rule and blah, blah, blah. Now B1, B2, and B3, the versors, are also fixed with respect to the body frame of reference. So if we take a derivative with respect to time, but of course, with respect to also the body frame of reference, there's no change. So B1, B2, and B3 do not change over time with respect to the body reference frame itself. So these 3 derivatives are 0. And also by writing so the derivative of the components of RB with respect to B, derivative with respect to time, of course, as RB dot, we have an expression of the non-inertial velocity of P with respect to the body frame of reference in the body frame of reference coordinates. So we found two velocities. These two velocities are different. One is an inertial velocity, which happens to be written in the inertial coordinates. And the other one is the non-inertial velocity, which happens to be written in the body reference frame coordinates. Of course, both inertial and non-inertial velocities could be expressed in either the body coordinates or inertial coordinates. And in fact, now we want to do exactly that. We want to express the inertial velocity, but in the body reference frame coordinates. So we have vi with respect to b, or better, the velocity with respect to I in the b coordinates. That's how you should read that. All right, so let's take the derivative of this vector. But now the derivative is with respect to the inertial frame of reference. So now these three derivatives, according to the chain rule, we have 6 components over here. And let's see if we can simplify something. Well, first of all, we recognize that dr, all these components are simply r dot b, r b1, r dot b2, r dot b3. So these are the rate of change of the coordinates of the position vector, of the coordinates of the position vector in the body frame of reference. And so if we take these 3, 1, 2, and 3 components, well, we recognize that we've just found, we just written the velocity, the non-inertial velocity in the body reference frame coordinates. Now, what about the remaining 3 elements of this expression? Well, we have that, we have these 3 derivatives, but these are not 0 anymore, because these derivatives, what we're looking at is the change of the 3 versors, b1, b2, and b3, with respect to time, but now seen in the inertial frame of reference perspective. So they do change. Remember that here I told you that b1, b3, b2, and b3 are time varying in the inertial frame of reference. So these 3 derivatives are not 0. So what is the value for these 3 derivatives? Well, we're going to see next time a little bit more in detail. Why is that? I'll just give you the conclusion now. But if you take the derivative of a vector, of a time-changing vector, the time derivative with respect to an inertial frame of reference, well, that is given by the cross product between the angular velocity of the non-inertial frame of reference, in this case b, with respect to the inertial frame of reference in the non-inertial frame of reference coordinates, cross product the vector itself. So let's say that our, let's start with the b1. So we have db1 over dt, referring to the inertial frame of reference, is equal to omega b slash I in the b coordinates. I know this is like, it's very long to just say all these terms, but I think it's also very beneficial because sometimes in several books you don't find many of these subscripts or superscripts, and you might get lost because you have the same I don't know, the same symbol, but you don't know which reference frame it refers to. You don't know the coordinates in which the vector is expressed into. So I prefer to be more clear and write down more things. So once you understand how to read these things, it's much easier actually to visualize than to read it out. Okay. So we have the cross product of the angular velocity times v1. So now you understand why we derived the angular velocity. It's because of this theorem, which is called the transport theorem, because we need that in order to find the derivative with respect to time of a vector. So now if we take the cross product, here I'm not going to go into details, I'm just going to point out the fact that the cross product of a vector with itself is 0, and then a cross product of b1 and b2, for instance, is b3. Then we have b1 cross product b3 is b2. And finally, b2 cross product b3 is b1. And of course, if you invert, so for example, a cross product of b is equal to minus b cross product of with a. So we have here b1 cross product b1 goes to 0, b2 cross product b1 is minus b3, and b3 cross product b1 is b2. So we find that this derivative has only two components in the b2 and the b3 direction. We can repeat the same thing for the derivative of b2 and the time derivative of b3. And please take a look at the details. And finally, we can write down the three components that we're missing, these three. Oops. Okay, so here we have the vector, but it can also be written as the cross product generally of the angular velocity cross product the position vector in the b coordinates. So now, after all this time, we come to the conclusion that the inertial velocity expressed in the b coordinates can be written as the non-inertial velocity in the b coordinates plus the cross product of the angular velocity of the non-inertial frame of reference with respect to the inertial frame of reference in the b coordinates, cross product the position in the b coordinates. Well, some of you could say, well, we had already the velocity in the inertial velocity. We just had it expressed in the I coordinates. Why couldn't we just apply a rotation to get into the b coordinates? Well, that is possible. The only thing is that, as I said, the inertial velocity in the I coordinates is difficult to get. It's much easier in general to measure the non-inertial velocity in the b coordinates and the position vector in the b coordinates, and therefore to find vbi, so the inertial velocity in the b coordinates, in this way. The only thing that is implicit here is the fact that the angular velocity itself is not directly measured. What you normally do, you measure the Euler angular rates and then applying this relationship over here. Well, first of all, you integrate the rates to get the angles. And then once you have the angles and the rates, you get the angular velocity. So this seems more complicated, but it's actually easier from a practical perspective. Now, of course, we can also write it in a more general way because vectors remain the same whether we express them in a reference frame or in another. So the inertial velocity expressed in any coordinate, so we don't have to express it necessarily in the b coordinates. So that is equal to the non-inertial velocity. So the velocity of p with respect to the non-inertial frame of reference plus the cross product of the angular velocity and the position of p. All right. So this is, I guess, a lot of information. So I'm going to stop here for today. Next time, we're going to see how we get to the inertial acceleration. We're going to look a little bit more into the transport theorem. And if we have time, we're going to talk a little bit about the so-called homogeneous transformation. So this is all for today, and I'll see you virtually next time. Take care.